Hello students, today we will discuss about one of the very important antennas in satellite communication, that is called as reflector antennas. So in this session we will discuss about what is a reflector antenna, what are the types, and what are the feeding structures, what are the dimensions, and what is the ratios we have to fix between focal length to diameter, and applications we will discuss. So what do you mean by reflector antenna? An antenna reflector is a device that reflects electromagnetic waves in the desired directions. Okay, the reflector means it reflects and it's going to converge a particular point. Why this kind of antennas are used? It is used for high gain, directivity, and microwave antennas. The application of reflector antennas are satellite communications, TV signal broadcasting, wireless communications, radio astronomy, parabolic microphones, and lighting device such as a car headlights, etc. So these are the different applications of reflector antennas. So what are the different types? This is the first type is it's a plain reflector. See here, this is the bold color line is called as reflector, the plain surface, and this is the feeder point, and signal is coming from the feeder and it reflects back to this and it will hit over the surface and it will be directed toward this front panel, right? So this whatever the signal hits over the surface, it will be directed toward this way. And this is reflector is called as corner reflector, and there are two plane waves are combined together and the feeder point is fixed over here. From this feeder point, the signal will be transmitted toward this plane reflectors and the plane reflector will direct. And this is parabolic reflectors where feeder point is here and signal will be transmitted from feeder point to the surface of the reflector, and the reflector will be, or the rays will be collimated, right? It is directed towards the front ray. And these all signals will be kept parallel because the incident rays from the feeder point is equivalent to reflector point, right? So plane of incident is equal to plane of reflection. So the reflector has been designed in such a way to transmit or collimate all the rays whatever is hit over the surface. And here there is another type of parabolic reflector, is called as Cassegrain reflector. Here two different reflectors will be used. One is the main reflector, that is parabola, and second one is the hyperbola reflector, that is called as sub-reflectors, and we have a feeder point. So the signal will be transmitted over here and it will be transmitted and hit over the surface of sub-reflector, and it will be transmitted toward this main reflector, and the signal will be transmitted toward this free space. And what is the drawback of this Cassegrain reflector? That is aperture blockage will happen. That is during this space, that is in this dimension, because of the orientation of the subreflector, it blocks the rays coming over from this main reflector. So this during this space, signal will not be coming out. So this is called as aperture blockage. And see here the animation shows about how the signal is coming from the free space, how it is converged towards this particular point where feeder will receive the maximum signal, right? So how this signal is received from this free space and hit over the surface of the reflector, and it is converged toward this point where if you locate a feeder point, it will receive a maximum signal strength, that is maximum gain we can achieve. So this is the way how the signal is transmitted from feeder, and this is the spherical wavefront to plane wavefront, how the signal has been converted. So this is spherical wavefront, and towards free space it has become plane wavefront. So the reflector will convert the spherical wavefront into plane wavefront in order to transmit a proper transmission path without any loss. And this is the radiation pattern of parabolic reflector. It is highly directional, and this is called as major lobe, where the maximum power has been concentrated toward this. So parabolic reflectors are mainly used for high directional antennas. And this is application of parabolic reflectors, and it is mainly used for satellite communications. It is a block diagram of how the signal has been received from the satellite and how it is distributed, how it is down conversion is occurred, and how the signal has been displayed over the destinations. So this is a simplified block diagram for television receptions with the help of parabolic reflectors. So these are the parabolic reflectors available. It is one of the it is some example, right? It is used for tracking systems, used as earth stations to track either some satellites in the free space. And these are called as prime focus reflectors, and this is Cassegrain reflectors. Cassegrain reflector already we discussed. The prime focus reflector, where the horn antenna will be acting as a feeder point, and that is used to transmit the signal towards the reflector surface. The reflector surface will collimate all the rays towards the destinations. And these are different types of feeders which is used in parabolic reflectors. The one is called as front feed, and this is called as with the help of horn antenna. This is a waveguide horn, and this is dual reflectors. It's a dipole feeder is used. This is called as offset feeder. The offset feeder can be adjusted vertically and horizontally. We can adjust. And Cassegrain feeder, where aperture blockage is occurred. And this is called as Gregorian feeders, and this is the inverse function of this Cassegrain feeder. And here also there are aperture blockage will occur. And what is spillover? Spillover is nothing but the leading into back lobe radiations, because the signal will be transmitted in undesired directions that leads back lobe radiations. The spillover has been reduced by using Cassegrain feeder, and the aperture blockage of Cassegrain feeder will be reduced by offset feeders. Thank you, students. Thank you.